Alright, so hello and welcome. Here we are again. We're going to validate a binary search tree, and this time we're going to use Morris traversal, and we're also going to do something kind of nifty. We're actually going to go ahead and not do this using recursion of any kind. We're actually going to do this in a way that's somewhat clever, in my opinion, depending on your perspective. What we're going to do is the following. So we're going to use now, first things first, I got this wrong, looks like over 2 years ago now. Yeah, in 3 or 4 months, it would be 3 years ago that I'd worked on this problem. Is that right? Yeah, maybe almost 3 years ago. So 3 years ago, oh boy, in Python. But we're gonna come back again in C++. And we're going to use Morris traversal, which by this point I have memorized, somewhat memorized. And we're going to do something clever. So, given the root of a binary tree, determine if it is a valid binary search tree. Valid BST is defined as follows. Left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. Yeah, simple. So that's sort of a simple definition for BST. And there are different ways to approach this, but we're going to take a simple one. So a valid binary search tree is, I'm going to give it a +1. A valid binary search tree, this is a kind of a classic problem. Valid binary search tree is, the in-order traversal must be a sorted list. So we can actually perform in-order traversal using Morris traversal to not use any extra memory, using threading and unthreading while we process each node, and we're just going to check in that in-order traversal, we're just going to check that the previous value and the current value, if the previous value is greater than the current value, then it's invalid, and we break early, return early, terminate early, otherwise it is valid. And that's it. Super simple. So let's try to code that up. We're going to say use Morris traversal to check the in-order traversal is yields a sorted list of elements. So we're going to say for, we have a tree node, which is going to be current, previous. Current starts off at the root. We're going to say while current, we're going to update previous to current, and we're going to update current to current right. And that's going to be our outer. Turn false. We're going to have check whether this is a threaded node. Current is a threaded node. So we'll say Boolean threaded is initially false. We're going to have another for loop. So if current, and we can say tree node r equals, it's actually current left. So if r, then we're going to have a for loop of r right exists, r equals r right, and we say if r right equals current, we're going to say threaded equals true, break, and unthread. Unthread the node. Current node isn't threaded. Then we will thread, and I'll thread every left node down to the node. if not threaded. So if you are, yeah, so right, something like that. So if not threaded, you have two loops, one inside of another, the other, and you're going to say current is going to be set to current left. Now, as long as we have a current left, we can continue. And we're going to say how this is going to work. So we do this for every node down the left side, and we update current appropriately. And we're going to say tree node R is going to be that node's left subtree. So whatever current node we're currently at, take the left subtree. We're going to say R and we're actually going to R right exists, R right, something like that, and then R right is equal to current. So a little bit confusing. So what's going to happen is, if we're not threaded, we're going to take this. You can imagine this happening just once in one routine. We take the left subtree, right? Set R to the left subtree, and then we're going to take the rightmost node of that node. So if there isn't a left subtree, so this guarantees there's a left subtree. So this will always exist. So there will always be an R right, and then you set R to that R right, and as long as there is an R right, then you keep going. As soon as there's no more R right, that's the rightmost node, and we can set R to. So what's interesting is, once there's no more R right, that means that R value is going to be the rightmost node, and then we can set the R right to point to the current. So we're going to thread, and then what happens is we update our current to the next node. So we thread all the way down the left sort of spine, I guess all the left nodes in sequence. And the way we do this is we find the rightmost node of each of those left subtrees and thread them back to the node that we just operated from. Once we get all the way down there, then we process our node as desired. So this will give us the Inorder Traversal. So here we'll say if previous is not equal to the null pointer, and previous value is greater than current value, then return false. Otherwise, return true. And that's it, I think. May have made a mistake somewhere in here. Let me check. Oh, it says it's true. All right. So it compiles. I think we got it right. Yeah, we update previous and current appropriately. So that should be fine. Basically, if the previous value is greater than the current value, so it should be ascending to check. I think that's all we need. Let's go for it. Oh, runtime error. Okay, what happened here? This also helps us to check. Also helps us to check that our idea about Morris traversal is correct. Helps us to check that as well. This is a little bit better than, I guess there's more test cases for our Morris traversal. So where does this get stuck? That's the question. Unless I coded this incorrectly. I don't think I did though. I may have made some error here. I wouldn't expect that though. This seems about right. I don't really need that. Okay. So 5, 1, 4, 3, 6. So this should be 1 on the left side, 5, and then 3, 4, 6. So this is false, but this gives us a. I could have tested some test cases too, but this is false. But also we get a have an issue here. What is the issue exactly? Deadly signal. Stack overflow, huh? Okay. So what goes wrong? Okay. So we get something goes wrong here. 5, 5, 4. Okay. 5, 5, 4. So it should actually go 5. So let's process the nodes. Let's do that. So 1, 5, 3. 1, 5, 3. That's correct. We should go back up to 4. So 5, 5, 4 is what we had before. Let me see. Let's just make this 2. I'm assuming maybe I just have the wrong, maybe I just coded incorrectly the Morse traversal, but I'm thinking the same code should work for both this as well as the previous problem we worked on. So first we start at 5, we drop all the way down to 1. 5 we should end up threading 1 to 5, and then we go down to 1 and then jump back to 5 unthreading 1, process 5, process 4 by threading 3 to 4, jump down to 3, process 3, jump to 4, it would unthread once you jump to 4, and then jump to 4, unthread 4, process 4, and then jump to 6, and then it should print 6. So where do we get stuck? That's the question. And one question also is like, did we just miss a test case that wasn't there in the other problem? Like that, I would be kind of surprised if this wasn't checked. Like if there's some case that I missed here. Oh, actually, I should do this. We won't be threaded if there is no left node. So where is this deadly signal happening? We get 5, 5, 4, 3 goes to 4, and then should come back to 4. What is happening? What's incorrect here. It's a stack overflow. Is it this? Is this overflow? I don't think it should. Could be that I just programmed these incorrectly. These are kind of error-prone loops, even if it's something that I like just programmed. Let's try this. Okay, 1, 2, 3, 1, 2, 3. So when we get to 3, current address 2, 4 should go to the right, yeah? Previous goes to 4, 4 goes to 6, and then we don't. So that's really confusing. Why, what happened? Oh, I think when we unthreaded, we did it incorrectly. Is that what happened? As long as we have a right side, we can update order right. Is it this that just keeps looping? Is that the problem? No, we don't print this one. We actually, it prints this and then it overflows. What? Is this the overflow? Is this part the part that overflows? That's really confusing. Okay. What is going on? What is happening? Okay, that's interesting. So test address goes back to 4. So 3, yeah, I mean, that's supposed to happen. So we process 3, we go back to 4. But why is it not printing the next one, this one? This one apparently is a problem. What's going on there? That's really confusing. I don't know if it's an optimization that's happening. I don't think so. What? Is it this part? Current equals current right? Hello? What is going on? No, we don't even get to the hello. What? Current address, test address. Is it this? It can't be this. Was it this? What is going on? I think there's something wrong with my while loop, or my for loop, my while loop, but... Oh, we get stuck here? What is happening? I am so confused. 1, 2, or 1, 3, 2. Excuse me. What is going on? I am utterly confused. This is new to me. This doesn't happen too often. So we get 1, 2. Oh, we're supposed to return false. But what? How come we can't just return false? What is going on? Yeah, 1, 5, 3. I mean, it should actually return on 3, really, not on 4 or 6. But what is happening? What is going on? It should return false on 1, 5, 3. It should be false already, but it's going to 1, 5, 3, 4. I am so confused. I am so confused. All right, first things first. Let's see. Do we traverse our what is going on? Is the compiler broken? What is happening here? Let's just comment everything out. Let's just print our current value. Let's start with that. Let's try that. Okay, 1, 5, 3, 4, 6. All right, so we get through everything here, right? Like that's okay. We're able to get through everything here. Confusing, but we get there. 1, 5, 3, 4, 6. All right. So it's not the looping structure. Like we're fine as far as the loop. Like we're okay. We're in good shape. That's not the issue. The issue is what is current and previous and current value. So if previous, then maybe I'm wrong. Maybe I did need to have is not equal to the no pointer. maybe I'm just maybe I'm just assuming things here. What is going on? So like I'm not crazy, you know. I'm okay. I'm as far as I could tell. I'm not nuts. Something really weird is going on here. There's something I'm not familiar with. So 1, 5, 5, 3, 3, 4, 4, 6. Okay. So can we say if previous and previous value is greater than current value? The node. All right. So there you go. So this should return false. Like we should just be done. Can we do that? Is that so wrong? Is that not what I just did before? Deadly signal. Excuse me. Excuse me. What do you mean deadly signal? How is that? All right. There's something going on with this program that I don't know what's happening. But that is bizarre. That is bizarre. All right. What is going on? It's deadly signal, Stack Overflow. Huh? What? What? Whoa. Okay. I was not expecting this. This is a very peculiar situation. So can we not terminate early? Is that the problem? If we try to terminate early, this will just give us problems? Whoa. Whoa. Not expecting that. I guess when you break, this will still happen. And it'll overflow? Maybe that's why? What is going on? Yeah, that's really weird. I was not expecting that at all. Does that happen if with a while loop? I think it's because of the for loop. Not expecting that at all. No, sir. What happened there? What happened there? That was really weird. So I'm kind of annoyed. I thought I did it right, and I basically had, as far as I could tell, I had it right. Let's see. Let's try it. Let's see if we're correct. Wrong. Okay. Oh, well, that's not fair. It says they're all less than, all greater than. Oh, well, actually, I guess it is fair. What did I say? I said, oh, I got true, expected false. Oh, I see. Got it, my mistake. If they're equal, that is fair, actually. I take it back. Take it back. If there are any duplicates as well. Okay, so it's okay. So that was pretty rough. Let's pump it up a few more times, see if we can get a higher score. Oh man, 19 milliseconds. Slow. Yeah, it's gonna be slower, I think, than because it's that's a Morris traversal is slower. Oh dude, how long did this take? 27 minutes. All right, let's go for one more. Brother, that was rough. That was rough. Now it's interesting. Okay, so this is correct. Now, what if I say return false instead of ret? How about that? Is that still correct? No, it won't work. It just says no. What about ret equals false? So that's really interesting. What is happening there? Excuse me. Wow. Now, if someone could explain that one to me, that is really bizarre. That is so strange. Why would that happen? That seems so bizarre. So it has nothing to do with the for loop. It has everything to do with, I guess, how this is being compiled. Is this because of GCC? Is this a compiler error? Whoa. Very interesting. Would not have expected this. Oh, I know why. I know what the issue is. Oh, that's very subtle. Oh, I see the problem. The reason why you cannot terminate early when you're performing the Morris traversal is because of the threading. Oh. Oh, I totally missed that. That's very subtle. That is very subtle. You need to finish you have to thread and unthread, because if I end up leaving a thread in there, then oh, I see the issue. I see. You can still somewhat terminate early by just deactivating any further threading. Oh, that's so subtle. Yeah. So what happened is I see what happened. we returned, and then the backend tried to validate the search tree after we returned, and there was still a thread, so it got itself into a loop, and that's where we got the runtime error. Oh wow, that's so subtle. That's so subtle. How to wreak havoc on the back end, on the how to wreak havoc on your LeetCode backend. Oh wow, that's super subtle, super nuanced. Okay, I thought I did it correctly. I was like, I'm pretty sure I did this right. Like, how did I? Oh wow, dude, that's wild. That is wild. That's pretty crazy. Okay. So this still works though. We do this. I think this is okay. Wow. Wow. Oh, I forgot that test case again. Shoot. Whoops. There we go. Pretty quick. Relatively quick. Careful not to terminate early. Must be careful not to terminate early. There are threads resulting tree moved. So actually, if you want to terminate early, you need to make sure you remove all of the threads. There you go, pretty quick, relatively quick. It's kind of interesting that it doesn't use, it's not optimal on the memory. Wasn't expecting that. Oh wow, the Python memory is less. That's weird. You'd expect less memory in C++. So another issue is, well, I guess it counts the memory you use from threading. That's probably why there's more memory. That's really interesting. So another approach. Another approach is, so how can we terminate early in this? So I was expecting this to be super quick, super efficient, very clever way of doing this, but not the case. It's not the case. We can, what can we do? Current node is a threaded node. Check to terminate early. If terminate, and continue. So I think we can say ret terminate equals false. Ret is true, terminates false. Ret is false. Terminate is true. Can actually, instead of terminate, we can say ret. If not ret, terminate early and remove any remaining threads. Very slight thing here. I think this works. Let's try that. Let's give that one a shot. Make sure we remove all of our threads. There we go. There we go. Okay. Wow. Very subtle, slight difference there. I would like to terminate early, but you cannot. You can't. I think it's better to actually not terminate early. Yeah, it looks like it's better to not terminate early because it adds an extra jump or an extra branch you don't need. You already have 3 branches here. Another branch just slows things down. If we're talking like milliseconds here. Wow, very interesting. Very interesting. So this is probably not as efficient as other approaches because it's iterative and doesn't use extra memory than what's already provided for us though, which is sort of optimal compared to the others. It's still also asymptotic. So asymptotically it's optimal in terms of the memory and the speed, but it's actually slower in practice I think than doing like if you use a stack-based approach. Because a stack-based approach you could terminate early, but you cannot terminate early when you're threading. So that's really interesting. That's a very subtle thing that I didn't realize. Also kind of annoyed now. This took 40 minutes to go through. I thought it was going to take me 5 minutes. Let me try it one more time. Let's try it one more time. Hadn't approached this problem in 3 years. Oh, there we go. Hey, 4 milliseconds. Sweet. Nearly got 100%. Yeah, I hadn't solved this problem in years, and I did actually see this relatively recently in an interview. I was annoyed I didn't have like a solid solution, and actually the interviewer did ask for an iterative solution, a solution that was iterative solution. So I could have whipped this out if I had practiced it, but I hadn't. But now I know it. Let me end this video. What I'm gonna do is I'm gonna start another one, see if I could do this in like 5-10 minutes. See how quickly I could do it. But yeah, thank you for watching, and let me try again.